Hello and welcome to today's lesson for Advanced Mathematics 1, Unit 1, Part 3, the properties of radicals or roots. By the end of today's lesson, you'll be able to do the following things. You'll be able to use the properties of radicals to simplify expressions. You'll be able to simplify expressions by rationalizing the denominator. And you'll be able to simplify expressions with rational exponents, which are fractional exponents. Our main concepts today are as follows. The square root of a product of two things, a times b, is the same as the product of the individual square roots. So the square root of a times the square root of b. This is true for any order root, so it could be cube root, fourth root, fifth root, etc. Basically, we have the same thing for a quotient. So this says the square root of a quotient of two things, a divided by b, is the same as the quotient of the two individual square roots, square root of a divided by the square root of b. There's an extra step, though, with quotients because we cannot leave a square root or any order root in the denominator. So we have to go through a process called rationalizing the denominator. What that means is we want to multiply by the same thing on the top and the bottom in order to get rid of the root in the denominator. So in the case of a square root like this, I need to multiply both the numerator and the denominator by the square root of what's in the denominator. So I have the square root of a over the square root of b times the square root of b over the square root of b. Square root of b over square root of b is 1, so I'm not changing the problem by doing this. So I'm multiplying by 1. And I end up with the square root of ab all over b, and the square root is done in the denominator. Basically, this is the same for every order root. It just means for higher order roots. So cube root, you would need to multiply by 2 more of the thing for a cube root to come out. So if you had the cube root of b, you'd have to multiply by the cube root of b and the cube root of b again. So you'd need 2 more cube root of b's in the denominator to get that taken care of. Last but not least, we have our fractional exponents or rational exponents. We have a to the b over c power means or equals the same thing as the cth root. So if c, the denominator, is a square root, we generally don't write the 2, but every other number we would write. So if it was a 3, we'd write the 3 as the index. That's what this is called. The little number in this little root box is called the index. To the a to the b power. So the numerator becomes the power of the number inside the radical. All right, let's go ahead and jump into our examples. In these first two examples, we're supposed to simplify the radicals. The first one we have is the square root of 2400. Now, basically, we're going to be using the property that says that the square root of a product is the product of the square roots. A lot of people teach you to simplify radicals by thinking of a perfect square that goes into this number, which is fine, but a lot of times you might not know the perfect square, and when you get to cube roots and fourth roots and fifth roots, nobody knows a bunch of cube roots and perfect cubes and perfect fourths. It's just too complicated. So I use prime factorization because it makes your life a lot easier. When you do square roots, you're looking for pairs of things to go in. Cube roots, you're looking for 3 of something. Fourth roots, you would need 4 of something, etc. So I'm going to do prime factorization. I do not prime factor the way most people do, which is by dividing out the smallest prime and then keep going up. It's kind of a pain in the butt, in my opinion. So I just think of 2 numbers that divide into the number that's there. So I have 24 times 100 is an obvious split. And then I keep prime factoring from there. So 24 is divisible by 4. It's 4 times 6. 4 is 2 times 2. And 6 is 2 times 3. For 100, I have 10 times 10. Now I could continue to prime factor this, but I'm not going to, because it's not really necessary to completely prime factor it. I'm just looking for pairs of things. And this is already a pair, so there's no point in going any further. So I have those 2 pairs. So anytime I have a pair, the thing that there's a pair of comes out. So there's a pair of 2's that comes out. There's also a pair of 10's that comes out. Everything that comes out gets multiplied by each other on the outside. Then I have the square root, and the things that there aren't pairs of stay on the inside. Again, they're going to be multiplied together on the inside. So I have the outside, which is 2 times 10 or 20, and the inside, which is 2 times 3 or 6. So that is how this thing simplifies. It becomes 20 square root of 6. In example 2, I have a cube root, and I have a special situation where I have a negative. You cannot take an even root of a negative number. A square root of a negative number is not defined, a fourth root of a negative number, etc. Any even number, because you can't multiply the same thing together an even number of times and get a negative number. You can, however, multiply something together an odd number of times and get a negative number. So anytime you have an odd root with a negative, you can separate out that root of -1 out front and then take the other number, which is 128. So you can separate it into those two pieces. The cube root of -1 is -1, and the cube root of 128 I'm going to do by, again, prime factoring. So I'm going to start by dividing by 4, and 4 goes in to 128 32 times. 32 is also divisible by 4 8 times. Now I'm not done with any of those. 4 is 2 times 2. This other 4 is 2 times 2. 8 is 2 times 4. And last but not least, this 4 is 2 times 2. Since this is a cube root, I need 3 of something in order for 1 to come out. So I have 3 2's here, and I have 3 2's here. And then this guy is left inside. So this group of 2's, 1 2 comes out. This group of 2's, another 2 comes out. And then I'm left with the cube root of 2 on the inside. We still have this -1 on the outside, so I'm just going to throw a negative out there. So I have -2 times 2 is -4 on the outside, and then I have the cube root of 2 on the inside. So this is how that simplifies, is -4 cube root of 2. All right, in our third example, we have this big thing in parentheses, all raised to the 1/4 power. So it's a fractional power. So everything to the first power on the inside of the radical, the 4 is the index of the radical. So this is a 4th root. So I'm going to start by just rewriting this as a 4th root. And it's this big old number, 576,240, x to the 4th, y to the 8th, z to the 7th. I crossed my z's, it's a thing. So for the 4th root of the number, I would do prime factorization. For the things raised to a power you want to divide. So basically you take the exponent and you divide by the index. The number that it divides goes out as the exponent on the letter. The number that's the remainder stays inside as the exponent on the letter. So 4 divided by 4 is 1. So x to the first comes out. For y, I have 8 divided by 4, which is 2, with no remainder. So y squared comes out. For z, I have 7 divided by 4, which is 1. So 1z comes out. And then on the inside, I still have this big number, so I'm going to copy that. So just excuse me while I do that. 6, 2, 4, 0. So 7 divided by 4 was 1 with a remainder of 3. So z to the third stays on the inside. So now all I have to do is simplify this big old nasty number. So I'm going to start dividing by 10 because that seems very easy to me. So 57024 times 10. and then I'm going to look at this number. So 24, the end digits, is divisible by 4. So that means the whole thing is divisible by 4. Divide by 4. It's 14,256 times 4. Obviously, 10 is 2 times 5. 4 is 2 times 2. 14,256. That's also divisible by 4. So that's 4 times 3564. And that, I believe, is also divisible by 4. So I can do, the 4 is 2 times 2. This is 4 times 891, which is no longer divisible by 4. 8 plus 9 plus 1 is 18, so that's divisible by 9. So this again is 2 times 2. 9 times 18. Unfortunately, that keeps going, so I'm going to, so right now I have 2, 2, 2, 2, 2, 2, 2, 5, 9, 18. A lot of things, sorry, so I'm going to do the 18 up here. 18 is 2 times 9. Doesn't make, oh no, it's not 9 times 18, I'm sorry. 891 divided by 9, I'm okay, is 99. So scratch all this. So I have 99, which is also divisible by 9. 9 times 11. So I have this 9, which is 3 times 3. This 9 is also 3 times 3. I know, this is a very big mess. So I'm looking for 4 of the same thing. So I have 4 2's here. I have 1, 2, 3 2's here, so that's not going to work. I have a 5 here. I have 1, 2, 3, 4 3's, so these 4 3's go together, and then I have this 11 that stays in. So altogether what comes out is a 2, a 3, that's all that comes out. I still have the x, the y squared, and the z on the outside, and then I have the 4th root of everything left on the inside. So I have 3 2's. I'm just going to write it like that. A 5 and an 11. So 2 to the 3rd times 5 times 11 is what that number is. And I also have that z cubed still on the inside as well. So that's 440. And then 2 times 3 out here is 6. So this is my final answer. It's a big old number. It doesn't look a lot simpler than it started, but you know, it's 6x y squared z, 4th root of 440 z cubed. So big long mess of a thing. So, you know, make sure you have plenty of paper, I guess. Fun. All right. Okay, now we'll move on to example 4. Example 4, we have a square root of a quotient. So we're going to separate that into the quotient of the individual square roots. So we have, the square root of 7 over the square root of 52. Now, I could start by rationalizing, just multiplying the top and bottom by square root of 52. That is not the most efficient way to do it. The most efficient way to do it is to simplify your square roots first and then rationalize last. So I'm going to start by taking 52 and simplifying it down. So 52 is 4 times 13. 4 is 2 times 2. So 2 comes out, and a 13 stays in. So in the top, I have the square root of 7. In the bottom, I have a 2 that comes out, and a 13 that stays in. So now I need to rationalize the denominator. So I'm going to multiply both the top and the bottom by what's in the denominator that's in the root. I don't need to get rid of that 2. That would be kind of silly. I just need to get rid of the square root part. So I need to multiply both the top and the bottom by the square root of 13. 7 and 13 are both primes, so there's not going to be anything that can simplify. So I'm just going to multiply 7 times 13 in the numerator, and that's the square root of 91 over, I have that 2 sitting there. Square root of 13 times square root of 13 is just 13. So my final answer is 2 times 13 in the bottom. So I have square root of 91 over 26. Final answer. All right, example 5, I have fifth roots. Again, I want to simplify first. So you're going to say, but the fifth root of 8 doesn't really simplify. And no, it does not. But it helps me in that I don't have to multiply by 4 more fifth roots of 8. That would be a pain in the butt. In order for a fifth root to rationalize, I need 5 of the same things on the inside. Right now I have 2 of the same things on the inside. So if I multiply by 3 more 2's in the inside, that will get rid of it. So I'm going to multiply both the top and the bottom by the fifth root of 3 more 2's. 1, 2, 3. And I am going to write them all out. 1, 2, 3. All right, and then I can just simplify that there isn't 5 of something in the numerator, so I can just multiply this out. 7 times 2 times 2 times 2 is 56. So in the numerator, I have the fifth root of 56. And then in the denominator, I have 5 2's, so that means that 2 is going to come out, and that's it, because the fifth root of 2 to the fifth power is 2. So there we go. That is example 5. All right, for our final example, we have a quotient involving a bunch of fractional exponents. All of the denominators are the same. All the problems will be like that. So that means that is the index of our root. So this is a cube root problem. So I'm going to rewrite it in the terms of those roots first to make it obvious what we're doing. So I have 18 up top, and then I have a cube root of both of these, so I can put them in one cube root. So I have w to the first power because its numerator is 1. I don't have to write the 1, I'm just writing it there so you can see what I'm doing. And then v to the fifth. And then in the bottom, I have 27. Again, I have another cube root. And I have w, its numerator is 4, and v to the first. So I want to start by simplifying those first before I deal with rationalizing. So I have this 18 out front that's just going to stay there. W to the first can't simplify because 1 divided by 3 doesn't have any divisors, but 5 divided by 3 does. 5 divided by 3 is a 1 with a remainder of 2. So 1v is going to stay on the outside and 2v's are going to stay on the inside. So on the inside, I have that w and 2v's, so v squared. And then on the bottom, I have 27, and then w to the fourth. So I have 4 divided by 3 is 1 with a remainder of 1, so 1w comes out, and 1w stays in. So that w stays in, and I also have that v that stays in. So now I'm ready to rationalize. So I have a cube root of wv. In order for that to come out, I need 3 w's in the bottom and 3 v's in the bottom. So I'm going to multiply both the top and the bottom by 2 more w's and 2 more v's. So I have 3 of each. Sorry about that sloppy v there. It's very hard to do this with a mouse. I don't have a touch screen, unfortunately, so I have to do the mouse method. All right, so up top, I have 3 W's, or 2 W's and 2 V's. Okay, so I have 1, 2, 3 W's. So a W is going to come out. I have 2, 3, 4 V's. So one of the V's is going to come out and one of the V's is going to stay in. And in the bottom, I have that 27. I have that W that's already on the outside. And now I have 1, 2, 3 W's, so another W comes out. And 1, 2, 3 V's, so a V comes out. So now I'm ready to simplify. So 18 and everything that's not in a root can simplify. So 18 and 27 are both divisible by 9. So this is a 2, and that's a 3. A W can cancel out of both top and bottom. A V can cancel out of both top and bottom. So what I'm left with up top is a 2 and a cube root of V. And in bottom, I'm left with a 3 and a W. Final answer. You really just need to take your time and go through step by step. That's all. See you next time.